this video I made to accompany the one that I did on vertex distance. I made a video showing you how to find compensated power or effective power when the vertex distance has changed. And it was basically theory, and I said in that one I didn't use the formula, the full compensated power formula. And I'm not really going to use it in this one either. All I'm going to do is show you where it came from, because that other one was basically about theory, and you probably want to use the full compensated power formula, but if you don't know how it was derived or what it means, sometimes it's a little bit harder to understand it. So that's all I'm doing in this video. In this video, we're going to use the very first scenario that we used in the vertex distance video, and that is a patient comes in wearing a +12 lens. The vertex distance is 10 millimeters or 1 centimeter, and they want contact lenses. And the first thing that we did is draw a picture up there in the right and determine that we needed to know the focal length of that 12 diopter lens. So we found the focal length using the focal length formula. We converted our focal length to centimeters because it's easier to work with. Now in this video, we're going to call this focal length F1, the initial focal length, the one that the patient came in with. And we're going to call the diopter power that they came in wearing D1. So they came in with a +12 diopter eyeglass lens, that would be D1 in this instance, and the focal length we found to be 8.33 centimeters, which in this case is considered F1. We also determined that when we moved that lens 1 centimeter, 10 millimeters, the vertex distance, in order to place the lens onto the eye, we eliminated that, but we moved the focal length along with the lens. So the focal length was now extended an additional centimeter behind the retina. So in order to get that focal length back to where the patient needs it to be to see clearly, we have to remove that 1 centimeter of focal length. And we come out with 7.33 centimeters, and we're going to call that focal length 2, or F sub 2. Okay, so what we want to find is our compensated power, the new diopter power, now that we've gone from a eyeglass lens to a contact lens and eliminated the vertex distance. So D2 is the power that we're going to need for a contact lens, and that's easy now that we know F2. D2 would equal 1 over F2. So that would be 1 over 7.33 centimeters, and it would equal 13.6 diopters. So we did ultimately find what we needed, which would be the power that the contact lens needs to be. But what we want to do is get all of this work boiled down into one single formula. So I'm going to start with what we actually want to ultimately find, D2. And in this case, D2 is the best effective power of the contact lens. So we know that D2 equals 1 over F2. We're going to substitute in for F2 the way that we achieved F2, which was by taking F1 minus 1 centimeter, which was our change in focal length distance. But we don't want to use 1 centimeter because that's specific to this particular instance, this particular patient. We want to use a variable for that because it may be, sometimes it might be 3 millimeters, sometimes it may be 4 millimeters. We don't know what it's going to be every time. So we're going to use the variable, and I put this up at the top because I'm running out of room. We're going to use the variable lowercase d to denote our change in distance, our change in vertex distance. And we're going to further substitute in for F1, our first initial focal length. We're going to substitute in 1 over D1, because most people don't know their focal length. When they come into the office, they don't know that they have a focal length of 8.33 centimeters, but they do know the power of their glasses, and if they don't, we can certainly find that out quick enough on a lensometer. So most people would know, for instance, that their lenses are a +12. So instead of but we wouldn't know our focal lengths. So we're going to have to substitute in there 1 over d1. Because we don't want to leave a fraction in the denominator of a fraction, we're going to multiply both sides by the denominator of that fraction, which will cancel out the denominator on the one side and leave just 1, the number 1 on that side. And on the other side, we multiply by d2. Now we'll divide both sides by d sub 2 to get that d sub 2 by itself, because that is ultimately what we want to find. And on the right-hand side of this formula, we now have 1 over d sub 1 minus lowercase d. Let's find a common denominator and subtract. And we're almost there, but I want d sub 2 all by itself, not as a denominator in a fraction, so watch what I'm going to do. And we found the formula. Now we can leave it this way, but because the book uses something slightly different, I'm going to just change it to the way that the book we're using has it, which is instead of d sub 2, they call it d sub c. And instead of d sub 1, they're using d sub l. Same formula, just a slightly different modification on the variable. And that's it.